Good morning, my name is Massimo Carbone. I'm working in the business development team for automotive, responsible for the e-mobility segment. Today I'm going to introduce you some system solution. In particular, we are focusing on the onboard charger, 22 kilowatt bidirectional onboard charger, and here we develop a specific power building block related to high voltage DC-DC converter. In particular, this converter that we develop is capable to manage 800 volt input voltage and 470 volt, 870 volt voltage range for the output. So let's make a step back. Talking about electrical vehicles, a very important component system inside the electrical vehicle is the onboard charger. Onboard charger can be unidirectional or bidirectional. Typically, the energy that is stored in the battery is utilized for the traction and for feeding additional system inside the car. But there are other applications, for example, outdoor activities, for example, energy back to our house, to the grid connected to our house. So in order to accomplish such type of requirements, you need to have the bidirectionality. Onboard charger, if you look at the block diagram, is mainly built with the three power building blocks. We have the AC-DC converter that is responsible to convert from AC line to the DC line, providing a pre-regulated fixed DC bus voltage. This is the input for the second power building block, that is the DC-DC converter, high voltage, 800 volt, and so taking the input voltage and providing a variable voltage depending on the status of the battery. In this specific case, can vary from 470 volt to 870 volt. And then the last component, the last power building block, is the DC-DC converter from high voltage, so interfacing high voltage battery, 800 volt, to low voltage battery, that in this specific case is 48 volt. So let's focus on the second power building block, so the bidirectional DC-DC converter, 22 kilowatt. So here we realize this system. The aim clearly is to show that thanks to the broad portfolio of Vishay and also to specific components that we develop, we can achieve a certain level of performance in this system. So in this specific case, we are talking about a converter that is taking 800 volt input voltage and 470, 870 volt output voltage. From power point of view, we realize this conversion utilizing dual active bridge architecture. Which is the advantage of this architecture, is the fact that using the DAB, basically you have a more symmetry power transfer in both directions. This is important because bidirectionality is a key feature. Second, you have a constant efficiency over a wide voltage range. That is our purpose. So we want to optimize this. This type of architecture is working in hard switching, so it's needed to have devices that are switching at very high frequency. And because of that, you need silicon carbide MOSFET, and Vishay just released silicon carbide MOSFET. And in addition to that, also from magnetics point of view, the dimensioning of the magnetics compared to other architecture, resonant architecture, is a little bit bigger. But on the other hand, you save because you don't have the resonant capacitor, so it's a kind of trade-off from component point of view. I would like to show. So let me take out, so this is the control board. This is the power board. So this system, using this type of topology, is allowing to have a very good symmetry also from hardware point of view. What I mean is that with the two full bridge topology, one on the primary side, one on the secondary side, you have done, let's say, the converter. The key point is that this type of topology also simplifies from a driving point of view the system. Let's look at the specific solution that we developed for this DC-DC converter. So we integrate the full bridge in one single module that is called MacPack. This will be released beginning of next year, and is using our high-density silicon carbide generation 2 of MOSFET, 1200 volt, 20 million. So in addition to the performance of the MOSFET, here we developed this package that is kind of trade-off between the traditional DBC exposed modules, well used in the industrial segment with the co-molded package. So co-molded package allow to have a very compact type of package. The form factor is optimized, the thickness of the modules is optimized, but the advantage taken from the industrial modules is that we don't have a frame, it's a frameless. So this means that every time that you need flexibility, so change the topology inside the modules, you don't need to spend a certain amount of money for the tooling, but it's enough to change the ceramic DBC substrate inside the modules. And this is the first thing. So you gain in terms of cost and speed of development. The other important thing is related to the fact that having the pins with the possibility to come out exactly near to the chip, you optimize the strain inductance of the modules. And so this means that the device can work at higher frequency with less EMI problem. And this is really an example of what we can do, understanding in detail the application and developing something that is optimized for that. So we talk about the power control. Let's talk also about the other components that are key in this application. So you will recognize on the power board the DC link in and out connected to the system. And here we are using our thin capacitor. And also you can recognize the ceramic capacitors that are used during the commutation of the silicon carbide MOSFET.